In this lesson, 2.1 static equilibrium, we are going to continue our discussion from 2.1 vectors. We're going to start out with a little bit of, I'm going to start with review, but we'll do a little bit of review as we go. And we're going to look at Newton's first law, take a look at what static equilibrium really means, and then we'll look at the equations associated with static equilibrium and then do some examples around that. So Newton's first law states that an object will remain at rest or in uniform motion in a straight line unless acted upon by an external force. So if we wanted to relate that to the work that we've done around vectors, we've been able to take a vector, actually more than one vector, so several vectors, and pull out the x components, add those x components together to get a resultant force in x, and then the same thing for y. We would pull out all the y components, add them together, and get a resultant component for y, and then we could draw a new resultant vector. And so essentially, if that sum of the x components or that sum of the y components were to be zero, were to equal zero, then that system with all of the vectors acting on it would be at rest. And so when we're talking about structures, or we're moving into trusses here soon, we really want the system to be at rest, because if it's not at rest, that means it's moving, and if it's moving as a structure, that's not good. So we're going to make sure that all of our systems are in what's called static equilibrium. And so let's take a look at an example, and I think it'll help to help you get your head around what we're looking at here. But we have a system here that has an eye bolt mounted into the ceiling. We have two vectors or two cables mounted to that eye bolt, and you can see that one's at 75 degrees down and to the left, and the other one, the blue one, is 20 degrees down and to the right. And we know from the last lesson that we can pull the x components of these two vectors, add them together, pull the y components of these two vectors, add them together, and solve for the resultants. And so the resultants would give us some kind of overall pull, maybe in, say maybe in this direction. But what we're ignoring with that is the fact that this eye bolt has to be able to hold 1,600 pounds in this direction and 900 pounds in this direction. It has to be able to oppose that. If it can't, if this is too much weight for the system, if it can't oppose that, then this system is going to fail, meaning that either the bolt's going to pull through the ceiling, or the beam is going to fail, or whatever it is. So we need to know how much this eye bolt has to be able to hold, both in the y direction and in the x direction. And so here we have the same drawing, but what I've done is I've put our equations in here. The sum of the forces in x is equal to 0, and the sum of the forces in y is equal to 0. And then I've drawn in two additional vectors here, one of them to represent the y component, meaning that when we take this y component, so we'll take this. We'll take this little y component here and this little y component here out of this vector and this vector. This has to be able to oppose those. So these are going down, and this one is going to have to pull up. The eye bolt's going to have to pull up to oppose that. And then the same thing in our x directions. But x, you can see I have one of them going off to the left and another one going off to the right. So to be honest, I'm really not sure if this arrow, this vector, should be pointing to the right or to the left, but I'm just going to assume that it's going to the right, and if the answer comes out negative for ax when we solve for ax, then I know that my assumption is incorrect. So, but we'll let the math work that out. We're just going to be consistent, and just if we're not sure what it is, we're going to assume it's positive, and then when we solve for it, we'll figure out if our assumption was correct. Okay, so solving static equilibrium is no harder than solving for the resultant vectors. So we're just going to use these equations here. Before we were just doing the sum of the forces in X. Now we're just doing the sum of the forces in X, and we're setting them equal to 0. So let's see what that looks like. So we know for X, since my angles are relative to the X-axis, cosine is what we're going to use to solve for the X component. So starting with, I'm actually going to start with the blue one here, the blue vector. We're going to take the cosine of 20 times the magnitude, right? So times the hypotenuse, which would be 900. Okay, so the cosine of 20 times 900 is the X component for this vector here. And just following along with my equation, I have to take the sum of all of the forces in X. Okay, so then I have this guy here, but you'll notice that it's going negative X. So instead of adding it, I'm going to subtract it because it's negative X. And then we're going to say the cosine of 75. And then times the 1600. And then I have the new vector here in X, which I assumed was positive, so we're going to add it, plus AX. And all of that has to equal 0. So when we do that, we find out that the cosine of 20 times 900 would be 845.72 minus, and then the this would be 414.11, and then I still have plus AX equals 0. And so if we were to work that out, we would find out that AX is equal to negative, let me get my calculator here, negative 431.61. So that actually means that my assumption here was incorrect, and that the reality is that in order to oppose these two vectors, the resultant of those two vectors, I would have to have 431.61 pounds going to the left in X. So we're going to take that out there. Okay, and now we're going to do the same thing for Y. So in Y, we're going to use the sine, and you'll notice that both of these are going down in Y, and then this one's going to have to oppose that by going up in Y. Again, I don't know that for sure, but I'm going to assume that AY is positive, and then if like we did, if it came out negative, we would know that we were wrong in our assumption. Okay, so we're going to start out with the sine of 20. We'll do this guy here, and then that's going to be times a negative 900 because it's going down in Y, and we'll go plus the sine of 75 times negative 1600, and then we're going to say plus AY equals 0. I'm going to have to move my screen over a little bit here. Okay, so just like that. Okay, so that's going to equal 0 there. All right, and so what we end up with is we end up with a negative 307.82, and that is negative, and then we'll have to say plus negative, or I guess we could just do minus. This would be minus 1545.48 plus AY equals 0. And when we carry that all over to the other side, we find out that AY is equal to 1,853.3 pounds. Okay, so that means we are correct in our direction here, 1,853.3 pounds. So what that means is with this pull here and with this pull here, we have to pull up. The ceiling or the eye bolt has to oppose 1,853.3 pounds in the Y direction, and in the X direction we see that it actually has to pull to the left 431.61 pounds. So if we were to kind of plot that out, we could figure this out here, that the new vector would actually look like that. And then we could use our a squared plus b squared equals c squared to get the magnitude of this guy here. So that would be the magnitude of our overall pool vector. So what we'll end up with, if we were to kind of redraw this thing, I'll do it very roughly here, but we would have the eyeball would have to pull in this direction, and the overall forces, this should be a straight line, meaning the resultant of these two are pulling in this direction, and you can see that they should equal each other. So this would be magnitude, we'll call this magnitude 1 and magnitude 2, and magnitude 2 would have to equal magnitude 1 because the sum of the forces have to equal 0. Alright, so let's take a look at another example here of static equilibrium. So I'm going to go ahead and since we can't see it up here, I'm going to write our equations in. We've got the sum of the forces in x equals 0 and the sum of the forces in y equals 0. And so down here what I have is, so let's call this F1 here a bar, and then F2 is going to be a cable, and then we have a load of 100 pounds that's acting on this system, whatever it is. It could be a bolt, it could be a pin, it doesn't matter what it is. But we've got a force pulling in this direction, a force pulling in this direction, and a force pulling in this direction. So right now we're going to use the sum of the forces in x equals 0, then we'll do the sum of the forces of y equals 0 and see what we can solve for. So starting here with x, we're going to write this out. I'm going to move up a little bit here. The sum of the forces in x, and what I'm going to do is I'm going to take the x component out of each one of these vectors and add them up and set them equal to 0. So in this case, here I have F2, which has an x component out of this vector, and that x component looks to be going in the positive direction, positive x, and then F1 looks like it's actually going to the left, so that would be negative x. So I'm going to start with F2 then, just so that I can start with a positive here. We know that since this angle is relative to the x-axis, we're going to use cosine. Alright, so cosine of 20 times F2, and that is the x component of this vector right here. And then since this vector has no angle, it's 90 degrees, or it's on the x-axis, then we can just simply add that vector onto it. So, but since it's going negative x, I can add a negative, or I can just subtract F1. And then we'll look at this guy here. This guy here is actually on the y-axis, so that means it actually does not have a pull in x at all. So we're not even going to count that in our equation because it doesn't have an x component. So here I have the cosine of 20 times F2 minus F1 equals 0. Only problem is I have two variables, so two unknowns, and I can't really solve for that. So let's go ahead and write in our equation here for y. Okay, so now just like we saw with this guy, this one only had an x, so it does not have a y. Therefore, it would not be included in the y equation right here. So we've got F2 looks like it's going positive in y, going in the up direction. The 100 is going down, which is negative y. So we're going to go ahead and write that in. So to get the y component of F2, we would use sine of 20 times F2. Alright, again that's positive because it's going up in the y direction. And then we're going to take this guy and subtract that out, so we're going to basically add the negative. So minus 100 equals 0. Now in this one here, sum of the forces in y, it looks like I can solve for that. I can solve in terms of F2. And then once I get F2, I can substitute that in up here and solve for F1. Okay, so sine of 20 times F2. So basically what this is going to come out to, we're going to move the 100 over here. So that's going to be basically, if I do it all in one step here, the F2 is going to equal 100 divided by the sine of 20. All right, and so if we were to do that, let me get my calculator here, 100 divided by sine of 20, that gives me 292.38. All right, so that came out positive, which is good. So we'll put that in pounds. That's good that it came out positive. That means that our arrow direction was correct. It is pulling up. It confirms that it's pulling up. So 292.38 pounds is F2. So once I know that, I can go up here and I can say, nope, you are 292.38. And then we can move F1 to the other side. So what we end up with is the cosine of 20 times 292.38 equals F1. And when we break that down, we've got the cosine of 20 times 292.38. Looks like we get F1 equals 274.75. All right, now that also came out positive, which is good because that we already had the arrow direction going negative. So that confirms if this number would have come out negative, so if that would have been negative, then that would have meant that our arrow direction here is incorrect, so we would have had to flip it. But since the numbers came out positive on both of these, that means all of these are in the correct orientation. And again, that just comes back to what we were saying earlier. If we don't know what they are, we just assume that they're positive. In this case, we assumed what's called tension, meaning that they're all pointing away from the joint, and they came out positive, which confirmed that all of these actually are in tension. We'll get more into tension and compression here soon when we get into truss calculations coming up. So I'll see you in future lessons. Let me know if you have any questions.